Hey, Chemsters, this is Mrs. Vanderwall bringing you a video to help you make good graphs. It is really important to make good graphs in science. We are analyzing data and looking at the relationships all the time. And you might think you already know how to make good graphs, that you've been making them in biology, you made them in physical science, you probably made them in your math classes. But I just want to be clear that we have the same rules and expectations for what I want you to do in chemistry class. So this is Mrs. Vanderway's rules for good graph making. So rule number 1 is always give your graph a title in the following form: the dependence of your dependent variable on your independent variable. So what the heck is that? Well, here's an example. Let's say you're doing a graph where you're studying the effect of temperature on the speed of a reaction. In this reaction, you are changing the temperature to known values. I emphasize you're changing the temperature. So the temperature is your independent variable. What you are changing is independent. Because you don't know the speed of the reaction, speed depends on the temperature. The speed of the reaction is your dependent variable. So if you're changing the temperature, how does speed, how is it affected by you changing the temperature? As a result, the title of your graph will be the dependence of the reaction rate on temperature, or something like that. So perhaps you can write down in your own words why temperature is independent, why reaction rate is dependent, especially given my huge hints. Go ahead and do that. Pause this, write down your answers, and I'll be right back. Okay, so why is temperature independent? Because that's what you are changing. That is the variable you are affecting. Why is reaction rate dependent? Because that's what you want to see. How is it affected by the change in temperature? So the reaction rate is dependent on the temperature. Before we go on, let me just make a little side note. If you ever are doing an experiment where time is involved, time is always the independent variable. You cannot affect time. Things are dependent on time. So that's just a good rule of thumb to keep that in mind. Rule number 2 kind of goes along with the first one. It says the x-axis of your graph is always your independent variable, and the y-axis is the dependent variable. So in the problem above, where the temperature and the reaction rate, you put temperature on the bottom with the x-axis, and you put along the y-axis your reaction rate. So what about time? Like I said before, time will always be on your bottom with the x-axis. Number 3, always give the x and y axes and label them and give units. So in the case of the temperature, if you're in degrees Celsius, and speed would be, let's say, so much per second, if you will. So you'd give your units. Number 4 is never, ever, ever connect the dots in your graph. Why? Because you're doing real experiment, you're finding real data. Real data is never perfect. All right, there's always some error, which we'll talk about later. So it says it's probably not a big deal, and it's frequently not something you have a lot of control over. That's your error. However, when you do an experiment, many little things can go wrong, and these little things do add up. As a result, the experimental never makes a straight line. Instead, it makes a bunch of dots, which kind of wiggle around a graph. So what is really important is make a line, all right, of best fit, and it's showing the trend that your data suggests. So as one's going up, is the other one going up in a linear fashion? Okay, so that's something that you need to think about. Finally, it says make sure your data is graphed as large as possible in the space you've been given. You probably have to know how many lines you have and your ranges of your X and Y data, and probably just divide your range by how many squares you have, and that will tell you roughly what each value of the square should be. Something else real quick about number 3 is that your axes should always have the same increment. Each square should always represent the same amount of time, the same amount of temperature, the same amount of whatever. So anyway, here are the steps you need to follow if you're going to make a good graph in your chemistry class. Here's some examples of good or bad. So let's turn the page. All right, so what I want you to do is take a look at this graph compared to our rules from the page before and come up with at least 4 reasons why this is a bad graph. So pause this and I'll be right back. All right, so why is this a bad graph? Well, number 1, there is no title to it. A bad graph is not a title. You might be tempted to say time versus temperature, something like that. That still isn't a good title. You need the dependence of something on something. Well, what's the problem with this graph? Do we even know what the X and Y axes are? Not at all. So we can't give it a good title. That's problem number 2, is that we don't know what the axes are. We don't know what the units are. That could be number 3. Number 4, we don't have a straight line. They connected the dots. It's a zigzag. It doesn't help us. I do think a couple things they did do right is that these are all in the same increments. Whatever this axis is going up by 10 every time. Whatever this axis is going by 40 every time. That is good. It looks like they used the whole graph. So they did some good things, but some bad things. Let's see an example of a good graph. Oh, this is what that graph is showing, the dependence of traffic ticket costs on automobile speed. So we do know what the x-axis is, automobile speed in kilometers per hour. We do know what the y-axis, it's the average speeding ticket. Would you have ever gotten that from this graph? Not at all. So you put down what it is, units, and notice they put a straight line here. So it's showing as the automobile speed goes up, as you're speeding worse and worse, what happens? Your average ticket goes up. All right, what I'd like to do next is talk about slope. Slope is rise over run, change in y over the change in x. So you know that the y-axis is on top and the x-axis is the bottom. And this idea of change, that is a capital letter delta, which means, change. How do you find that? Final minus initial, or the second point minus the first point. And so you work through it this way. It says helpful hint. If your graph does go through the origin, use this as a point to solve for slope. So here is an example. And we go ahead and number 1, 2, 3, 4, 5. I left off the 7, I guess. 6, 7, 8. And now we can find slope. Now I know this graph has not been labeled. I don't know what x and y is. That's not the purpose of this. The purpose of this is to find slope. So let's go ahead. So if we have point A, look at A right here. A goes through the origin. So I can make this maybe my point 2. Look how it nice and hits the slash marks here. And make this my point 1. That's why there's a 1 here already, all right? Because that's my point 1. So can we find the slope of A? And I'm hoping you say, well, yes, we can, because what's the y value of point 2? My y value is 6. Minus, well, what's my y value down here at the origin of point 1? That's point 1, right? 0. It's going through the origin. Well, what's my x-axis here? Well, if I go down, it is 8. That's an 8 there. All right, minus 0 again. And that's 6/8 or 0.75. Okay. What about slope for B? Why don't you go ahead and take a look at B here. Why don't I go to a blue dot here, and you come up with what you think slope is. All right, so if you find slope B, I picked these 2 points. Did you have to pick those 2 points? No, those are the ones I picked. Hopefully you got the same slope. So I picked my y value is 8 minus 0. Notice it's still a 0. And then my change in x is 5 minus 1. So if you look, that's 8/4, which is equal to 2. So my change in y is, I'm using purple, 8. My change in x is 4. If you look at it, isn't this 2 changes of y to 1 change in x, 2 changes of y to 1 change in x? Yeah, so the slope is 2. So let's go ahead and find the slope of C. Why don't I use green for that? So here I'll use this point and I guess this point. And see what you get here. Do it on your own. All right, so using this as point 1 and using this as point 2, my y1 is 7, my y2 is 0, my x2 is 0, my x1 is 6. So if you do the math, you end up with 7 over -6, which is -1 and 1/6, which is -1.16 repeated. So notice that this is a negative slope. So if it ever looks like this, that's a negative slope. If it ever looks like this, it is a positive slope, all right? So which line has a negative slope? Obviously it is C. The smallest positive slope, well, these two are both positive, so my smallest one, hopefully you got, is A, and the greatest is B. All right, so your turn. Why don't you go ahead and construct the graph below using the techniques shown above. Go ahead and pause this and spend some time, work it through so you draw your graph, draw your best fit line, and find your slope, and then stop. All right, so look what I've done here. Here is the title, The Dependence of My Y Distance on Time. That's my dependent variable, my independent variable. My time is my y-axis, my distance is my, I'm sorry, is that right? My time is my x-axis, my distance is my y-axis. And my best fit line may not be your best fit line, but I thought I did a pretty good job. I made this my 0.2 and I made that my 0.1. So I went up here to find the slope, y2, which is 30 minus 0, divided by 50 minus 10. So it looks like 3/4. And if you look at this, yep, my rise is 3, my run is 4. So that makes sense, so 0.75. As far as the equation goes, do you recall the slope-intercept form of an equation? Well, here it is. So do you recall y equals mx plus b? So what I want to do is I want to plug in values for that. So watch what I do here. So I just plugged in one of my points. I used 0.2. So y is 30 equals the slope I just found up here, 0.75, and I'm going to use 50 as my x plus b. I don't know what my b is. I got to figure it out. But if you look, if I draw this line down here, don't you notice that it's going to be a negative y-intercept? So if I plug in my numbers, that is what happens. All right, so I plug in my numbers. 30 equals 37.5 plus b. B is negative 7.5. So when I'm all done, that is my equation. As far as the relationship goes, all I'm going to do is substitute my y and x value. So all I did was put distance as my y. See, my y is distance equals 0.75 times x, which is time, minus 7.5. Now that is meaningful to me. All right, let's see what the next page brings. Why don't you go ahead and work on this problem, and I will have the whole thing done for you when you are done with your problem. So pause this, work out the whole thing, and then come back. All right, so this is what I came up with. I went ahead and I labeled my graph, as you can see there, and I kind of cheated, and even though the point was 20.2, I just made it on top of my graph that way. And then I put my points. I put my point here and up here. And I put my line of best fit. And what do you notice about that line of best fit? It goes through the origin. So I was smart, and I made that one of my points. And that's my point, my 0.1. And I'm looking, where did it cross the axis? And I thought this was a really good point right here, which is 19 as my mass and my 7 as my volume. So I did label it, the dependence of mass on volume. So if I was actually doing this experiment, I was actually changing the volume and seeing how the mass responded to that. So this is my my independent variable. I was changing the volume. How was mass affected? So then I went ahead and I found slope. So y2 minus y1, x2 minus x1. I use, again, this point in the origin. So I use 19 and 0. And then I went down and find out that was 7. If you want to look down here, 7 and 0. So that's 2.71. Found my equation, y equals mx plus b. Y equals 2.71x plus 0. How come it's 0? It goes through the origin. That's where it crosses the y-axis. Boy, my life got easy. And so I didn't have to solve for b. I'm looking at it and I know what b is. And then here is my equation. Find the relationship. This is where I plug in, well, what is what is y? It is mass. What is x? It's volume. So what does this tell me? No matter what the volume is, I'm going to multiply it by 2.71, and that's going to be my mass. So if my volume is 1 down here, all right, my mass is about 2.71, and look at it. That's what that tells me, and that is the strength of doing it this way. It's very, very beneficial. I hope this helps. go ahead and do your homework now. Thanks. Bye-bye.